What's the role of chemical engineers in the future of energy and sustainability?
So the way that I see it, it was chemical engineers that basically created our current fossil fuel-based energy industry in the 20th century, right? I mean, the oil and gas-based technologies are all hardcore chemical engineering. How do I take this chemical resource and turn it into energy in various forms? And we've seen that we need to change these things now, and one of the most promising technologies that is emerging is our solar cells. So again, chemical engineers can play a key role in this, together with material scientists and engineers, by creating the materials that allow us to capture solar energy and turn it into electricity and replace that 20th century fossil fuel-based industry.
Did you know that solar power is one of the most powerful sources of renewable energy? In fact, the sunlight that shines on the Earth in just 1 hour could meet our world energy demand for an entire year. But how do solar cells work? Solar energy can be used to make electricity. The process of making electricity from solar energy is called photovoltaics. A photovoltaic cell has many parts, so let's start by breaking down the anatomy of a photovoltaic cell, otherwise known as a solar cell. Solar panels are made up of individual solar cells. In 1881, Charles Fritz created the very first commercial solar panel. In 1939, Russell Ohl created a solar cell design that is used in many modern solar panels. By 1954, this design was used by Bell Laboratories to create the very first commercially viable silicon solar cell. Two silicon layers take up a large part of the photovoltaic cell. Most of the action takes place between these two silicon layers. Next are the metal conductor strips that conduct the flow of electrons of the energy produced by the cell to the system being powered. On top of the cell is an anti-reflective coating, which makes sure that the photons, the particles of sunlight that are used to generate solar power, are absorbed by the silicon layers. Without this anti-reflective coating layer, the photons would bounce off the cell and no energy would be produced. So where does this process start? Let's start with the silicon layers. Light from the sun becomes energy for us to use between these two layers. Since silicon is a poor conductor, the layers have to have something added to them for electrons to flow. To make the layers a better conductor, engineers add a little bit of another element into the silicon, usually boron and phosphorus. This is referred to as doping the two silicon layers. The red layer, the layer with the phosphorus added, has more electrons than the silicon would by itself, while the green silicon layer with boron added to it contains less electrons. This is important for our solar cell to produce energy. Next is the generation of an electric field. An electric field is needed to produce electricity. Remember how the phosphorus layer in red has more electrons? In an electric field, opposites attract, so the more negatively charged red side and the more positively charged green side attract each other. In this case, the electrons on the red side move to the green side. This is why it's important that the two sides are in contact and the process happens very, very fast. After the extra electrons have moved to the green side becomes negatively charged where the two layers meet. Now that we have an electric field, the cell is ready to accept the photons from the sun. When the sunlight hits the cell, the photons begin to push the electrons loose in the silicon layers. At this point, the electrons are free to bounce around within the layer. However, these electrons do not create electricity until they get to the area between the two silicon layers, because the electric field pushes them through the top layer and to the metal conductor strips. Once these electrons are launched to the metal strips, they flow into a wire to something called an inverter, a device that turns the current from the solar cell into a current that can be used by the system you're powering. In order to maintain electricity, the system must be closed, which is why electrons also flow back into the system.